In today's class, we will go over a problem on sedimentation. But first, we'll look at a poll question. When softening water with a high hardness to the stoichiometric limits, 30 milligrams per liter as calcium and 10 milligrams per liter as magnesium often remain in the effluent. Why is this the case? We've got several options. I'd like you to read these and then vote using the poll question. You may choose more than one correct answer.
Is because, one, the solubility of calcium carbonate and magnesium hydroxide, which is what we're precipitating, is such that roughly 30 milligrams per liter of calcium and 10 milligrams per liter of magnesium remain. But there's also other issues. Okay? One, there may be short circuiting in the reaction basin, and that can be a cause. And then, unlike acid-base reactions, precipitation reactions take time. And there may or may not be sufficient time in the reaction basin for precipitation to be complete, or for those reactions to be complete, and therefore some calcium and magnesium remains. So operator error, there may be operator error, but that's not the reason for the 30 milligrams per liter of calcium and 10 milligrams per liter of magnesium, and the original statement is correct. And what I would like to do then today is we're going to do a grit chamber problem, but we're also going to look at how sedimentation fits into wastewater treatment. We talked predominantly about water treatment so far, but this should help in turn, especially for those of you that are in 495 this semester and are actually doing a wastewater project. We have wastewater that enters from the sewer system. The first process that we have is some sort of screening. And I apologize again for the line. So we have bar screening or bar screens. We may have what are referred to as a grinder or a comminutor. Okay. These are devices that take the larger material. This can be flushable wipes, which are not flushable, okay, and cause major problems in wastewater treatment systems, cause problems clogging in sewers, pump stations, etc. These need to be removed before treatment. The effluent from that then goes into a grit chamber. So the grit chamber is essentially a sedimentation basin, which is what we'll look at today, that removes fairly large material. So this can be sand that's gotten into the sewer system, eggshells, coffee grinds, anything that is relatively large, typically about 100 to 300 microns in size. It's mostly inorganic material that we're removing. We're trying to keep the organic material in suspension. We want essentially inorganic material, non-biodegradable material to settle in this grit chamber. And you can see a picture of the grit material. In many cases, this material is actually washed, and that wash water is pumped back to the head of the treatment plant. And then that means that grit material contains less organic, it's not going to degrade. So that material isn't going to degrade. It's not going to go anaerobic. Often this part of the plant is actually the smelliest part of the plant. So that the grit is typically landfilled. The effluent then goes to a primary sedimentation basin. These are the primary sedimentation basins from the East Lansing wastewater treatment plant. And here we have a launder. So this is our launder right here. We have a notched weir, and the water flows over the notched weir into the launder, would then flow into a main collection channel. In this image here, you see the scum that's floating on the top. Typically, in these systems, it's often a flight and chain system, but you also have a scum collector on the top that pushes the scum into a scum trough, and then that can be further treated. The sludge from that is then further processed, often dewatered and thickened. So this is our sludge. And our effluent then goes into an aeration basin, which we'll talk about later in the semester. Oxygen is added to that. What we're doing in that system is using microorganisms to degrade the organic material. So we're looking at converting the complex organics into CO2. Okay. We also convert ammonia into nitrate, and if we have denitrification, N2, we convert hydrogen sulfide, H2S, to sulfate, and often will precipitate phosphate. So what we're trying to do is convert that material that would consume oxygen in the receiving body of water in the aeration basin. Okay. The effluent from that, which is actually referred to as mixed liquor, then flows into a secondary clarifier, and you can see them here. The one on the left is from the East Lansing water treatment plant. The one on the right is from the Williamston water treatment plant. East Lansing treats about 9 mgd per day, Williamston about 2. Difference really is processes that they're handling are essentially the same. Color differences really have to do more with lighting than anything. Typically, we're looking at using a circular clarifier as a secondary clarification process. Now, the sludge from the secondary clarifier, some portion of that is returned back to the aeration basin, and that's returned as return activated sludge that contains high concentrations of microorganisms, and we need those microorganisms to degrade the organics in the aeration basins. And then some portion is wasted, and that is referred to as waste activated sludge, and that would go on for further treatment, typically thickening, dewatering. We can look at a thickening basin. Again, these are typically circular clarifiers. And here, what we're doing is we're trying to remove water from the sludge so that we essentially reduce, so that we reduce the volume, but we also reduce the costs of further treatment or disposal. And from there, the effluent then may go through advanced treatment, and we'll talk about that later. That can include filtration, typically then some sort of disinfection, and then discharge to the receiving body of water. And you saw the discharge outfall for the East Lansing plant in the scavenger hunt. Any questions about wastewater treatment? just a little overview to kind of give some context of the problem that we're going to work on today and help those of you that are in 495. Okay, I'm going to add the link again, just in case anyone missed it. Okay. So what I would like to do today is we're going to work through this problem with a grit chamber. Okay. So we have a horizontal flow gravity grit chamber. It's designed to remove spherical particles having a diameter of 1.71 times 10 to the minus 4 meters. So about 170 microns. The depth of the grit chamber is 1 meter. The detention time of the liquid in the grit chamber is 60 seconds. The particle density is 1,830 kilograms per meter cubed. The water temperature is 12 degrees C, and the maximum daily flow rate is 0.6 cubic meters per second. So I'd like to put you in groups. Question that I have is, do we have anyone in the classroom? And if so, how many people do we have in the classroom? Patrick, you're usually my classroom person. Are you in the classroom? And if so, how many are with you? Okay, so I will put you then in your own breakout room. And then I will put everyone else in breakout rooms. So just give me a few seconds. I'm going to keep the breakout rooms shorter today. So we'll have more breakout rooms, but we'll spend less time each time in the breakout rooms. So let's do 4 breakout rooms. I'm going to assign manually. So you'll be in the breakout rooms for 5 minutes. What I would like you to do is just the first 2 problems. If you can want to go on beyond that, that's fine. Determine the overflow rate and estimate the terminal settling velocity. So quite a few of you are already in the Google document. So keep you in the breakout room for 5 minutes and then we'll process this. Okay. The overflow rate is equal to the flow rate divided by the surface area. It is also equal to the height divided by the detention time. And in the sedimentation lecture, I go over the derivation of those equations. So that is equal to the 1.0 meter depth divided by the detention time, which are given as 60 seconds. So that is 0.0167 meters per second. Okay, the terminal settling velocity is equal to G times the difference in the density of the particle and the density of the fluid times the diameter of the particle squared divided by 18 mu. Now, this is Stokes' law, but there are several assumptions in this version of Stokes' law. So the assumption is that the particle is spherical, and I mentioned that these were spherical particles, and that the Reynolds number is less than 0.5. So we've made that assumption implicit in using this equation, which is why I have said estimate. Problem is we don't know Reynolds number, because in order to know Reynolds number, we need to know the terminal settling velocity of the particle, which is what we're solving. And in order to use the general equation, we would need a coefficient of drag, which we also need the Reynolds number. So we're kind of in this catch-22. So we need to make these assumptions estimate the terminal settling velocity. So if we do, this is 9.81 meters per second squared times the density of the particle minus the density of water at 12 degrees C times the diameter of the particle. And in the homework, make sure the particle sizes are given in microns, so make sure you convert those to meters. That's squared, divided by 18 times the dynamic viscosity, which is 1.235 times 10 to the minus 3 Pascal seconds, and that is equal to 0.0107 meters per second. Okay, so we've now estimated the terminal settling velocity. What I would then like you to do is to determine the Reynolds number for the particles, answer the question, is Stokes' law, this version of Stokes' law that we just used, valid? And if not, provide a better estimate of the terminal settling velocity. So I'm going to put you back in breakout rooms. We'll spend about 5 minutes working on this problem in the breakout rooms. And then I will bring you back to go through this. So determine the Reynolds number for the particles. And the Reynolds number is equal to the diameter of the particle times the terminal settling velocity times the dynamic viscosity, or sorry, the kinematic viscosity of the fluid. So the diameter of the particle is 1.71 times 10 to the minus 4 meters, that's given. The terminal settling velocity we just estimated as 0.0107 meters per second. We'll divide that by the kinematic viscosity, so this is 5, times 10 to the minus 6 meters squared per second, and that is equal to 1.48. Now 1.48 is greater than 0.5, so that means we need a more accurate equation to determine the terminal settling velocity. So the answer is no. So what we can now do is we'll use that Reynolds number that we just calculated to calculate the coefficient of drag. And that is equal to 24 divided by R plus 3 divided by the square root of R plus 0.34. And if we substitute in for R that we just calculated, that is 24 over 1.48 plus 3 divided by the square root of 1.48 plus 0.34, and that is equal to 19.01. So we can now use that coefficient of drag and the more accurate equation for the terminal settling velocity. It's the first equation that you have on the spreadsheets. And that is that terminal settling velocity is equal to 4g times the difference in the particle density and the fluid density times the particle diameter divided by 3 times the coefficient of drag times the density of water. And if we substitute in, then that is 4 times 9.81 meters per second squared times 1,830 minus 999.5 times the diameter of our particle. I apologize for these lines today. Times 10 to the minus 4 meters divided by 3 times 19.01 times 999.5 kilograms per meter cubed, and that is equal to 0.0000989 meters per second. Okay, that gives us a better estimate. However, it's still an estimate. Now that we have a terminal settling velocity, we can use that to iterate on a solution. Then we can take that value here, calculate a new Reynolds number, use that new Reynolds number to calculate a new coefficient of drag, use that new coefficient of drag to calculate a new terminal settling velocity. And we can continue to do that until the terminal settling velocity converges on a solution. And you can do that by hand. You can do that on Excel, just manually, or you can do it using Solver and solve where the solution converges. Okay. My advice is if you do not have Solver as an add-on onto your Excel, add it. It'll make your life much easier with many of these problems. Okay. So the next question that I would like to ask, and I'm going to do this next part without a breakout room. Again, I apologize for the breakout rooms. But given the time, let's just go through this together. So the next thing I'm asking you to do is to determine the percentage of the particle removed. So for a horizontal sedimentation basin, the percentage removed is equal to the terminal settling velocity of that particular particle divided by the overflow rate. And if we were to draw a sedimentation basin, okay, we have particles that come in at different velocities or different depths. So this particle here comes in and it's removed. This particle is also removed. However, this particle, same settling velocity, escapes. If this were an upflow, well, let's calculate this first. So if we continue, or if we use Solver to determine the terminal settling velocity, let's see if I can get rid of some of these lines. I apologize. It appears to have something to do with how stable the internet is at home. And we divide by the overflow rate. That is equal to 0.554. So roughly 55% of these particles are removed. If this were an upflow clarifier, what percentage of these particles would be removed? So this is true for a horizontal sedimentation basin. Circular clarifier, it's also true for that. But if it were an upflow clarifier, so an upflow clarifier operates, the water flows in through the center. This center is our mixing flocculation basin. It then flows upward. So this is the bottom. There's a hopper at the bottom. The water flows upward and then out a weir at the top. Okay. And we have a sludge blanket here. So it flows up through the sludge blanket and then out over the weir. So same overflow rate. If we have the same overflow rate, the same particle settling velocity, what percentage of those particles are removed in the upflow clarifier? The answer is 0%. In an upflow clarifier, only particles that have a terminal settling velocity greater than the overflow rate are removed, and those are removed at 100%. Anything with a terminal settling velocity less than the overflow rate are not removed at all. So it's 0 or 100%. There's no fractional removal with an upflow clarifier. So the next thing I asked you was to determine the length and width of the grit chamber if the length to width ratio is 3:1. So if you remember, our overflow rate is 0.0167, and that is equal to Q times the surface area, which is Q times the length times the width, and the length is equal to 3 times the width. So that's equal to Q times 3 W times W. And if we solve that, the width is equal to 3.46 meters, and therefore the length is equal to 10.38 meters. The last thing I asked you, and I kind of went through that quickly because of time. The last thing that I wanted to ask, that I've asked you, is to determine the horizontal velocity in the chamber. And this is equal, so the horizontal velocity is equal to Q times the cross-sectional area, and that is 0.6 meters cubed per second. The cross-sectional area is our height or depth, width, and that is equal to 0.6 divided by 1 meter times 3.5 meters, and that is equal to 0.17 meters per second. So we now have the full design of a grit chamber.